Now we're going to turn our attention to conduction current, which is a form of current that I think we're all a little bit more familiar with. So in this case, we need a conductor, or in other words, a metal, to have this conduction current. So let's sort of go back to basics again and see if we can't derive an equation for our conduction current density. So let's start by considering the force on free electrons. So force on our free electrons, and so I'm just going to write E minus for electrons, is given by F is equal to negative Q times the electric field. So whatever electric field it's in, we multiply by the charge of an electron, and that's going to be the force. And so one thing to note notationally, this negative Q, like I said, is just going to be the charge of an electron, so 1.6 times 10 to the minus 19 coulombs. In the textbook, they use, and so let me write this out explicitly, so charge on an electron, in the textbook, they use negative E. So just one slight change there if you're reading through the textbook as well. So let's call this equation up here for our force equation 1. And so we can also get the force from a different approach by considering Newton's second law. So we can say from Newton's second law, we have F equals ma. So force equals mass times acceleration, where of course acceleration is just our velocity divided by time, right? So meters per second per second. So we've taken that meters per second of velocity and divided it by time. And so let's call this equation 2. And of course, you can kind of see where I'm going here. We have two equations with force, so let's just equate those two. So let's equate our two different equations there, and we can say then that we have mu over our t is equal to negative QE. And so I'm going to make one other sort of adjustment here as well. Let's say that we use a specific time. So let's say we're going to use time equal to a specific time tau. And so this time tau is something called the mean time between collisions. So mean time between collisions. And so what this represents is, of course, if we think about our atomic structure of our metal, we have a bunch of nuclei, we have the electron clouds, and so as these electrons are being forced through this material by some electric field, they're colliding with the atomic lattice, they're interacting with the electron clouds, and so what this mean time between collisions is sort of the average time between these collisions. And so what we can say is that it's accelerating for a time tau, at which point it basically resets, the velocity goes back to 0, and then it's accelerating another time tau until it has another collision event. And so to reflect that, let's just go ahead and replace that t in our equation with tau, and again, this tau is our mean time between collisions. So we're not going to get too much into that mean time between collisions other than just that basic definition. So from that expression, we can solve for our velocity. So we can say the velocity of these charges then is going to be equal to negative q tau over m times the electric field. And so a really cool thing that we can do is we can actually relate this back to something that we talked about in our analog devices when we were looking at semiconductor physics. So this term that relates our velocity to the electric field is actually our drift mobility. And so our drift mobility, remember, is indicated by mu in this case because we're talking about electrons. We can call this mu sub n. And so let's call this equation 3 to be consistent with the notes. So now what we can say is, of course, we don't just have one electron, we have a lot of electrons. So let's say we have n electrons per unit volume. So for n electrons per unit volume, we can talk about the charge density. So the charge density is given by our rho v is just equal to negative q times n. So it's how much charge do we have on each one times the number that we have. And so that's going to be the number of charges per unit volume. again, because our N is defined as electrons per unit volume. Okay, so let's call this equation 4 to be consistent with the notes. And so now what we can do is we can take equations 3 and 4 and we can plug that into the general expression that we saw in the previous video for our convection current. And so remember, we said that was sort of a really general case we were going to use for conduction current as well. And so here we are. So we can now say that our J is equal to rho V times velocity. So that was our general equation that we saw in the previous video. And so now we just plug in our two equations 3 and 4. So we can sort of combine those two and we get that we have N, which is that electron density, times Q squared times tau, the mean time between collisions, divided by the mass, all of that times our electric field. And so it turns out that this term in parentheses is our very special value of conductivity, sigma. And so that is equal to sigma times E. So again, of course, all of that turned out to be our conductivity. And so for the most part, we're not going to be going down to these units again. We're just going to be dealing with a specific value for sigma. But I think it's kind of cool to see how this relates back to how we've approached this differently in other classes. And so using this equation, this J equals sigma E, so if we have J equals sigma times E, this is actually known as the point form of Ohm's law. So as we expect, Ohm's law should work for our metallic conductors, even though we saw it didn't work for our convection current. And so what we're going to do in the next few videos then is start looking at how our metals are going to behave in electric fields.